So hello, here me again. So we have learned about some basic of the optimizations. We know how to formulate the optimization problem, and then now just try to see how we can solve unconstrained optimization problem. Yeah, I think you've seen this several times already. So we are here. So we are going to solve. We're going to learn this part for today. I'll repeat again on the necessary and sufficient condition for optimality briefly, and then we have several methods to solve the one dimension or one variable unconstrained optimization. So necessary conditions for optimality is that the first derivative equals to 0, right? So the first derivative equals to 0, and then if you make them equals to 0, and then you can find the x value that either maximize or minimize that function. And then the sufficient conditions is that we do the second derivative. If the second derivative is then positive, that means we have the minimum functions, and if it's negative, we have the maximum functions. The same goes if we use the multivariable with the Hessian matrix. So there's a special case where if the variable is single variable functions, and then both first derivative and second derivative equals to 0, and then we can use like a successive higher derivative, so we derive it further and further until it is not 0, So if the this is then the nth time that we derive it. So if this nth, for example, if the n is even number, is a maximum. If it's even number and then the value is then negative, it is a maximum. If it's positive and then it is minimum, like normal, right? But if the n number is then an odd number, like and then the x is then the saddle point. So it means in this case we don't have a maximum or nor the minimum point. Now here you can just try it on your own. See if these functions have an extremum, either minimum or maximum. You can see it here. Yeah. If fx equals to x to the power of 4, do they have an extremum? We derive it once again. This equals to 0. X also equals to 0. You know that the stationary point at x equals to 0. And sufficient condition is then the second derivative, which is then 12x squared. This is also 0. Yeah. So if it's 0, we don't know if it's positive or negative. So we continue to higher derivative. So we derive it even further. So 24x and then 24. And this 24 is the fourth derivative. Since 4 is the even number and 24 is positive, that means this is then a minimum functions. Yeah, you can apply. This is a one case. So I forgot in the previous slides that we have case studies at the end. So I think you could also revisit them and try to solve the case on your own. And you can always come back to me if you have any difficulties in that. Yeah, try to solve it. So we have here we have like a knockout drum. We have a compressor, very simple one. So one of your colleagues changed the demister, and the new demister has this efficiency functions. Yeah, and then with the same flow rate, they have a different performance. So you can now recommend to your boss what would then be the correct new velocity with this new demister. So how to solve it? How to find that? How to find the value of x in such a way that the objective function is minimum or maximum? In general, there are two major types of approach. Number one is then what we call as function value. So in this case, we just like you see in our previous examples, that we just vary the value of x in such a way that we can then calculate the objective functions, and then we compare it with the other objective functions, so that we can see either the other one is then bigger or smaller than the other objective functions. One of the methods in here, we call it bracketing method. We'll go through what that is. And the second one, we call it derivative based method. So if we can derive the objective functions, so we can use this approach, Newton method, secant method, and any other methods that using the derivative based approach. Yeah. So approach number one is we don't need to derive the functions. Just we could say it like a bit of trial and error, and we compare if one value is higher or lower than the other, then we can then decide our next step. The second approach is then derivative based approach, where we have to derive it. So the function value, like I say, so we have just initial guess, and then we calculate the objective function based on this value, and then we change this value x0 to x1, yeah, by anything. Either it's random, or you have like you own your own algorithm, for example. So for example, could be like delta x 0.5. So if this is then 1 and then delta x is 0.5, that means this x1 is then 0.5. Sorry, this is 1 and this is then 1.5. And you calculate again what is then the fx1. If the new fx is lower than the current fx, that means we are moving in the right directions, right? In this case, because we want to minimize it. Yeah, I forgot to mention this in the beginning. So we want to minimize it. So we have to make sure that the new value is always less than the previous value. And then we know that we are moving towards a minimum point, which makes sense. So when can we stop? Yeah, we stop when either if we moving towards the lower and lower, and then at some point the new value give us like a higher point. That means we can stop here. Yeah. Or if we have like if we use like delta x small enough, and then the new, I mean, for example, if we come across a function where we stuck already, I mean the difference between the new value and the old value is then less than our error tolerance, we can also stop. So for maximization, we could also like minus the objective functions and then minimize it. A bracketing method is then based on that function value method. So we know that at this point, this is then the x. So at this point we have a minimum. Yeah, so we have this value, that value, this value, and that value, for example, another value here. So we know from here and there it's decreasing, and then from here it stays constant, that decreasing. So it could be that in this area we have some minimum value. So these two lines are we call the bracketing. So and then in this case we then try to make the delta x smaller, so that we can see if this minimum point is there or not. Yeah. So that's what it means by these three statements. So take a look at this example. So fx equals to x minus 100 to the power of 2. So this is then our algorithm to find the new x. So xk plus 1 equals to xk plus delta 2k minus 1. So you can make your own algorithm. It's no problem. So if we use delta equals to 1, and then we start at x1 equals to 0. So x equals to 0, that means this is 0 minus 100 to the square is then 10,000. Yeah, minus 110,000, and x2 is then x1, which is then 0. So 0, and then this is then 2. 1. 1 delta is then 1. 2 is then 2, and then k is then the second iterative. So 2 minus 1, so it's 1, and then the So 2 to the power of 1 is 2, so it is then this is an error typo. So 0 plus 2 is then 3 in this case, yeah. So you can calculate then, so this number is then not correct, but then you can calculate that. So if we put x2 equals to 3 and then you put it there and then you calculate the f, you get the new value here. Maybe this is then the number 9409. And then the same goes if we then now we have x2 equals to 3 and then you put also 3 over here. So you have to repeat these calculations again. The 3 and then calculate again, and then you get maybe this is then the new number, and so on and so forth. So you can see that the objective functions is then decreasing until here, and then now it increases. So from here to there, yeah, somewhere in these 2 points, at 63 and 255, somewhere in these two, they have a minimum point. So we put our bracket over here. So that's one, the minimum range, that is the maximum range. And then we can just change this delta, for example, and then try to make it try to make the step is smaller, try to make the step more smaller instead of this formula. So it is quite double the size, and that's double the size. So make it smaller, and then you then find minimum objective functions within this range. So that was the object function value, where we don't have to derive it. So the first on the most well-known method, a derivative base, to find to minimize or to optimize is then the Newton or Newton-RAPHSON. We know this from our previous knowledge on how to find the root of a function. So now the relation between this Newton and the optimizations, we can then relate them to the first derivative equals to 0. So that necessary conditions for optimality. So in order for our functions to be minimized and maximized, we need to find the stationary point, or the point at which it is then it has like a peak. So these necessary conditions, or the peak points, is then at f, the first derivative equals to 0. So now we know that Newton is able to find the root or the equations of this. So the value of x in such a way that the f, the functions of, in this case, the first derivative of the functions equals to 0. So you can see if we have these functions, and then the first derivative is this line. So the first derivative equals to 0 as at this point. And then we can see if we start from this xk, for example, xk, so the value of x, the first derivative of f is in here, this xk, and then we want to find this xk plus 1, which should be equals to 0. And then you can see that the slope of this line is then that functions, this function fxk minus fxk plus 1 which is then equals to 0, and then divided by the delta x from here to there. So this is then the slope, and this equals to the second derivative of the line. And then if we rearrange this to get the new x, we get this and then that. Just to rearrange these equations. So if we have initial point, we have the first derivative of the functions, we put that initial point there, we can calculate this term, and then the second derivative of the same functions, you put that number into there, we calculate this, and we can then calculate the new x. And that new x, we put them again to the same equations to get the xk plus 2, and so on and so forth, until we see the difference between the xk plus 1, and the difference between the new x and the old x is then less than the tolerance that we have specified before. Then we stop the algorithm. For example, so we have these functions, x squared minus x. So we start x0 equals to 3. You can start with your own number as well. So x0 equals to 3. So the first derivative is then 2x minus 1, 2x minus 1. So put 3 here. 2 times 3 is 6, minus 1 is then 5. And the second derivative is then 2 in this case. Yeah, it won't change with any value of x. We plug it into that equations. So the new x is then equals to all x minus the first derivative divided by the second derivative. So 3 minus 5 divided by 2 is half. So this half, we put it back to the same equations. So put this half into here. So 2 times half is then 1. 1 minus 1 equals to 0. And then x1 is then half. Half minus 0 divided by 2 is also half. So this half is the same as that half. So in here, we can just stop the iteration. So we have converged. So that means at x equals to half, we have an optimum value. Okay. Another, if we don't know, I mean, if we in some functions, we cannot derive it. Yeah. So instead of doing that directly with this function value, for if we don't want to do any derivations, we could also tweak this Newton method a little bit with this what we call like a finite difference Newton method. So it has the approximations of the first derivative and the second derivative. So the new x is then the old x minus, you can see this is the minus, and then this is then the approximations of the first derivative with a new term of h, or the step value, which you can define it on your own, and then divided by the approximations of the second derivative, yeah, for one variable. So in here, we don't need to do the derivative, just use this formula. By varying the value of h, you can then calculate how much or how big the new x changes with the old x. Another method is then the secant or quasi-Newton method. So it is different from the Newton method where we use one initial point. In this case, we have two initial points, xp and xq. So when we put this into the first derivative of the equations, fxp and xq, they should have like opposite signs, which means somewhere along this xp and xq, the first derivative of that x should be equals to 0. So if we have this xp over here, the first derivative is over here, which is then the plus, right? Plus. And then if xp is over here, that means the first derivative of this fxp equals to is a negative term. So this negative, and that is then positive. So somewhere along this line, as you can see it here clearly, there is a 0. And then you can then calculate the slope, yeah, which is then fxq minus fxp divided by xq minus xp. You can then rearrange this to get the new xp equals to xp minus the first derivative of xp and multiplied by this slope. And then you can get the new xp, yeah, the new xp, so that it will then eventually as close as the x star or the optimum value. And here you can make like a find the minimum value of this. So you can use like an Excel or whatnot. So if we have this objective function x4 minus x plus 1, the first derivative is 4x3 minus 1. So in this case, as you can see, it doesn't use the second derivative. It uses only the first derivative. So you use the first iterations, you specify what is then the initial value of xq and the initial value of xp. Calculate the first derivative of xq, first derivative of xp. So it's a positive, this is negative, so we are good to go. That means there is somewhere in between a 0. Calculate the m and then calculate the new xp and then calculate the new fxp. So put this number there, yeah, put it there, and then here put it back to the new, and then so on and so forth until you get it converged. So we've discussed on the Newton finite difference where you on Newton where you have to have like first and second derivative, finite difference where you don't need any derivative, but the second method you need only the first derivative. So this is just like this two is a variant of the Newton method. So please solve this using these three methods. Yeah, try to do it on your own first and pause this video. So if I put this, if I could use these three approaches in Excel, I would get this one. So Newton method. So I have initial value of 3, second derivative, first derivative, and second derivative. So I iterate that until like you can see it's yeah, maybe like 6, 7, and 8 iterations. You get 8 iterations, for example, 7. So we get it is now converged. So the value of x is then 1, yeah, it doesn't change anymore, and then the first derivative equals to 0 already, which is at the at an optimum point. And with the finite difference Newton, if I use h equals to 0.001, so I calculate that fx plus h, fx minus h. So at the iterations of here also approximately the same iterations, the x value is now close to 1, x is then 0. Yeah, so these functions, the objective functions, is already 0. And the quasi-Newton secant, xp is minus 5, xq is 3, and then until we do the iterations until this also quite more than 20, maybe 30 or so. So we are, yeah, I mean, if you see this still 1.00 something, it has something. But if you say that if your convergence is then 0.001, if it's 0.001, so that means in here, yeah, and here you converge already. If your tolerance is 0.01, that means this is converging points already. Yeah? 0.01 is bigger than this number. So these examples you can do it on your own with these examples, with these three methods. This is another case study that you can do on your own. So we have like a simple distillation, simple a column. So we have liquid feed and then the product, and then we have a reboiler with the oil in and out in a temperature of 150 degrees C, and then this has a broken thermocouple, yeah, which happens in practice. And then the efficiency of the column, it says according to boil up rate, yeah, and this is then the efficiency. Somehow the operator is very intelligent that he can make for you this kind of efficiency equations, where x is then the boil up rate. Heat of evaporation of the product is 2000 kilojoule per kilogram. Yeah, so we have this product, and some part of the product we boil them up, and then to boil them we need to have 2000 kilojoule per kilogram. And then the operator also says that oil has a capacity of 3 kilojoule per kilogram Kelvin, and then the delta T here is only allowed for 50 degrees C, so 150 degrees C and 100 degrees C over here. So it has the flow meter of the hot oil, and it has the temperature of the hot oil measurements. Yeah. So the question is then how much you have to boil the oil so that we can have we can have our product in the highest efficiency as possible. I think that sums up our module for today. So see you next time.